Have you ever stopped to think about how the ones and zeros on your computer screen just magically travel through the air and turn into a video on your phone? It's kind of amazing, right? Well, today we're going to decode that invisible language. We're going to see how simple bits are transformed into the waves that literally power our modern world. So let's dive in.
It really all comes down to this one fundamental question. We think of data as these abstract things, just ones and zeros sitting on a computer. But to actually send that data anywhere, to stream a movie, to send a text, it has to become something physical. So how does that leap happen? How does a number become a real signal that can cross the country in the blink of an eye?
The answer is we shape waves. We take a nice, consistent, predictable signal, we call that a carrier wave, and we start changing it or modulating it. We can mess with its frequency, we can shift its phase, or, and this is our focus for today, we can change its amplitude, which is really just a fancy way of saying its height or its strength.
And this gets us right to the heart of the first major hurdle that communication engineers had to figure out, what we call the digital to analog problem.
See, here's the thing. Computers speak a digital language. It's a language of separate, distinct values, 1 or 0, yes or no, on or off. But the physical world, the world of radio signals and electricity moving through a wire, that world is analog. It's all smooth, continuous, flowing waves. So the huge challenge was, how do we translate the blocky, distinct language of digital into the smooth, flowing language of analog?
Well, the very first solution to this problem was just brilliantly simple. Instead of trying to invent something totally new, engineers decided to just change the height of the wave as it was moving along.
And we call this technique Pulse Amplitude Modulation, or PAM for short. The core idea is super straightforward. You just take a series of pulses and you make them different heights, different amplitudes to represent your digital data. It's pretty much the most direct way you can imagine to embed ones and zeros into a physical wave.
In its most basic form, it works just like this. You've got your signal. To send a 1, you send out a pulse with a high amplitude. To send a 0, you send one with a low amplitude. High, low, high, high, low. You are literally drawing the digital code as a physical waveform.
And this works. It's a solid system. But you know where this is going. As the world started demanding more and more data, a really important question came up. Is sending just one bit at a time with one single pulse really the best we can do? To go faster, you just have to send pulses quicker and quicker, and that eats up more and more bandwidth. So the real question was, could we make each individual pulse carry more information?
And the answer to that question was a huge yes. It came from this incredibly clever shift in thinking. What if we add a second dimension to our signal? And this is where we meet the absolute powerhouse of modern communications, QAM.
So with PAM, we were just adjusting one thing, the height of one wave. Think of it like a single-lane road. Information is flowing, but it's just one car at a time. Quadrature amplitude modulation, or QAM, is like building a second lane for a data superhighway. It uses two carrier waves at the exact same time to carry two separate streams of information.
So how on earth does it do that? Well, it takes two carrier waves on the exact same frequency, but, and here's the magic trick, it shifts one of them by 90 degrees. This little phase shift makes them orthogonal, which is a fancy way of saying they can be mixed together for the journey and then pulled apart perfectly at the other end without ever messing with each other.
The best way to think about it is like a graph. You've got your first wave, the in phase or I component. That's like your x-axis, your left and right. Then you've got your second wave, the quadrature or Q component. That's your y-axis, your up and down. By changing the amplitude of both the I and the Q waves, we can now define a unique point, a coordinate, on a two-dimensional plane. And this idea, this ability to define coordinates, leads to one of the most beautiful and powerful ways to visualize data in all of engineering, the constellation diagram. Let's check it out.
Okay, first we got to learn a new piece of vocabulary, the symbol. Remember with PAM, one pulse meant one bit. Simple. But with QAM, a single unique state of the signal, so a specific combination of I and Q values, can now represent a whole group of bits. And we call that unique state a symbol.
So what's a constellation diagram? Well, it's literally a map of all the possible symbols we're allowed to create. Each dot on this map is a valid coordinate, a target that the transmitter can aim for by setting just the right I and Q amplitudes.
Let's start with a really simple example, for QAM. Here we have just 4 possible points, 4 symbols. So we can assign a unique 2-bit sequence to each point.
0, 0, 0, 1, 1, 0, and 1, 1. Now think about that. With every single pulse, every symbol we send, we're now transmitting 2 bits of information instead of just 1. Bam! We've just doubled our data rate without using any more bandwidth.
But why stop at 4 points? This is what makes QAM so powerful. Let's make that map a little denser. What if we create a constellation with 16 possible symbols? Well, with 16 unique points, we can now represent every single possible combination of 4 bits.
That's right, 4 bits per symbol. Just let that sink in for a second. We went from a simple on-off pulse to this 16-point map, and in doing so, we've quadrupled the amount of information we can stuff into the exact same moment in time. We've doubled our efficiency all over again.
Okay, so we've journeyed from these simple up and down pulses to these complex star charts of data. But what's the actual payoff here? Why does all this elegant math and engineering matter so much in the real world?
At the end of the day, it's all about one thing: efficiency. The airwaves, the fiber optic cables, they all have a limited capacity, a finite bandwidth. Denser constellations like the 256 QAM or 1024 QAM used in your Wi-Fi router and your 5G phone let us squeeze an incredible amount of data into that limited space. This is the engine. This is what drives high-def streaming and lets you download huge files in seconds.
Of course, you knew there had to be a catch, right? There's always a trade-off. As you pack more and more points onto your constellation map, those points have to get closer and closer together, and that makes your signal much more sensitive. Just a tiny bit of random noise or interference can make the receiver mistake one point for its neighbor, and boom, you've got an error in your data. So it's this constant engineering challenge, this balancing act between the need for speed and the need for a clean, reliable signal.
And that kind of leaves us with this one big final thought. We started with a simple pulse that could carry 1 bit. We've now moved to these incredibly complex constellations that can carry dozens of bits at once. And as our world's appetite for data just keeps growing and growing, the real question is, how much denser can we make these maps? How much more information can we ultimately pack into a single, invisible wave?